At this point in our analysis, I think it would make a lot of sense to take a pause and just think over what we've done. We've been looking at second-order homogeneous DEs, and again I want to reinforce this is with constant coefficients. With that general class of problems, this is all the AY double prime plus BY prime plus CY equals 0. What can we do with that? Well, what we're going to do immediately is, through our assumption, y equals e to the rx, we're going to get a characteristic equation, which is AR squared plus BR plus C equals 0. We are going to get a characteristic equation, and the roots of that are going to tell us what R should be in this formula. However, we found it's not quite as simple as just finding R and then using it, but we have some nice guarantees. There are always going to be two roots to this, guaranteed. If it's a second order, if it's a quadratic, we're going to have two roots, R1 and R2. Well, if that's the case, we're going to have R1 and R2, and if R1 and R2 are real, so no square roots of negative ones, and they're distinct, in that scenario, well, we can build two solutions. We have y is equal to c1, whatever the first guy is, plus c2, what the second gal is. That'll be our general solution. Two different exponentials, and they're going to be linearly independent because they're two multipliers for the exponent that are different. However, if we have R1 equals to R1, so real but repeated roots, we've seen that's possible, straightforward to have that happen, then what are we going to get? Well, let's just call this R if they're both the same. We'll have e to the rx, of course we will, because that's what we sub in here, but we'll also have the same idea, e to the rx, but multiplied by that x out front. And we showed that that was also a solution, but only in the case when we had a repeat. So we somehow had to use e to the rx twice, but we couldn't use the same thing verbatim. Multiplying by x turns out to be the way to get a second linearly independent solution. Last but not least, if our two roots end up as a complex conjugate pair, which means they have the same real part and also the same imaginary but with the sign flipped, for that scenario, we're going to have a constant times the real part ends up in the exponent, e to the ax, and whatever ends up with this square root of -1 multiplier, you take the real part, so you ignore the square root of -1, and take just the real part and put it inside a cos, or alternatively, you take it and put it in front of a sign. And I cannot convey how exciting this is. This is amazing because this is all the possibilities. If you look at the roots to a quadratic characteristic polynomial, quadratic polynomial of any kind, there's three things that can happen. You can have two different real roots, or you might have the roots that are real but they actually end up at the same value twice, or they end up with a square root -1 when you do your quadratic formula. That's it. We have covered every single possibility for a second order linear differential equation because we know exactly how to solve every single possible second order quadratic equation without derivatives, simply finding roots of the quadratic formula. This is going to pay dividends throughout the rest of the course, and I would like you to keep your eye on this idea that somehow there's distinct cases, repeated cases, and complex roots showing up lead to these exponentials that are simple, exponentials that are then scaled by something, and then exponentials mixed with sines and cosines. This pattern is going to arise a number of times through the course, so keep your eye on that as well. With that procedure in mind, let's take a stab at analyzing a scenario like this. Notice again, this is an IVP, an initial value problem. We've got our initial conditions in addition to the differential equation itself. So we know that we're going to assume y is equal to some exponential with a coefficient r that we don't know yet. That's going to lead to the characteristic equation. And that characteristic equation, in this case here, is going to be 16r squared minus 8r plus 145 equals 0. Every derivative, 2 of them here, gives us an r. One derivative, one r. No derivatives here means no r, but just a constant. Now, no one wants to solve this by hand by trying to factor it manually, so what we're going to do is use the quadratic formula, because we have a nice quadratic. So r is going to equal minus b, so that'll be plus 8, plus or minus the square root of that squared, minus 4 times a times c, which is 145, square rooted, all over 2 times the leading coefficient, the 16. That boils down to 8 plus or minus. If we work our way through the calculations here, we end up with the square root of negative 144. And it's all over 2 times 16 is 32. Well, that we can tidy up to be 8 over 32 plus or minus. Well, this is 12 in disguise with a square root of negative 1. If we took this 12 and multiplied it in, we'd get 12 squared and a negative make it negative 144. And that's all over 32. So just tidying up a little bit, we have a quarter plus or minus, dividing by 4, we get 3 over 8 square root of negative 1. This is exactly the a plus b times the square root of negative 1 form that we identified earlier as being an interesting case. And right away, we can write down the general solution. These imaginary parts of the root give us sines and cosines, and the real part of the root, the 1/4, give us exponentials. So y would equal some constant, e to the real part, 1/4 x, so the 1/4 times the x, and then the imaginary part goes inside, so the 3/8 goes inside a cos, again with an x multiplier. And then we repeat it again, coefficient times x, and then the sine of the other half of the coefficient, 3/8 here, times x as well. So that is an excellent landmark to pause at and admire the solution. This is not something we would necessarily have guessed in any way, shape, or form based on what we saw in the original equation, but if we have faith in our methods, this would be a solution that we could sub in and verify that it works. In this particular question, we're more interested in using the initial values here to solve for. Notice again, we always have our C1, C2 unknown constants. These values will let us solve for those. We'll do that on the next page. Here is our general solution. Here are our initial conditions. So what we're going to do is just sub these in and solve for C1, C2. This initial condition here is quite easy to solve for. The y starts at -2 when x is equal to 0. Well, you just got to be careful with this. We'll do this one in detail. We'll see patterns as you go through these over various examples. We don't need the 3/8 because x is going to be 0. And here you just have to remember that sine of 0 is 0. Cos of 0 is the more interesting value. At 0, it equals 1. And so right off the bat, we get C1 equals -2, which isn't bad at all. It does get a little uglier when we look at the second initial condition because it's all about the derivative, which means that we need to know what y prime is. Well, that means taking our general solution here and taking its derivative. If we do that, this case is the most complicated because it has the product rule, it has an exponential times a cos, so we're going to get quite a long derivative here, but it's straightforward, just a little tedious. We're going to have C1 times e to the x over 4's derivative is 1/4, e to the x over 4 cos, and we also have, the product rule says we've taken the derivative of the first check, now we need the first by itself, times the derivative of the cos. The derivative of the cos is negative sine. We also get a 3/8 popping out. And that's about all we're going to fit on that line. And then we're going to throw in a C2, all the same ingredients, same product rule because we're differentiating the exponential times sine. The only thing that changes is that sine cos ordering. And the fact that the derivative of sine is positive cos. We still get a multiplier, but we have a positive cos of 3/8 pop out. Then we can sub in the point at y prime of 0 equals 1. We're going to have 1 is our y prime. And here I would just look through and go, thank goodness this value is a 0, not something worse. E to the 0 everywhere, e to the 0, e to the 0, e to the 0 is going to equal 1. And cos of 0 equals 1. And sine of 0 equals 0. So we're going to be able to simplify a number of these way past where it looks like right now. We'll have C1 times a quarter. And this one, because it has a sign, will just be 0. And then we'll have plus C2 times a quarter. Wait, no, that's times 0, so we get rid of that. So not times that. But we will have a 3/8 times 1 times 1. So at the end of the day, we end up with this, but fortunately we know what C1 is. So let's put that in next. We'll have 1 equals minus 2 over 4 plus 3/8 times C2. That's a negative a half, so we'll have 3 halves equals 3/8 of C2. 3's cancel. Bring the 8 up, we'll end up with C2 equals positive 4. And that means that our final solution is going to be based on, and here just remember where we put C1. C1 went with the cosine. So we're going to have C1, which is minus 2 exponentials x over 4s times the cosine of 3/8 x. Now we're going to have a 4 times the e to the x over 4 times the sine of 3/8 x. And that is the particular solution to the initial value problem. Where the initial conditions were given, we use that to solve down for the initially unknown coefficients in the general solution. The key step in this process being the connection between the characteristic equation and its solution, which ended up being a complex conjugate pair, and being able to associate that result to the form of the solution being a mix of exponential and sine and cosines.